So that Bernard is.
Yeah.
Okay, so I think we'll start. We have the talk today will be part of a series of 3 lectures that Ketan Marmali from the University of Chicago will give on his approach, his algebraic geometric approach to P versus NP. So, Ketan, you're ready. This talk today will be a little longer than usual, like an hour and 15 minutes, unless you ask questions. And then the talks tomorrow and Wednesday will be more elaborate, 2 hours each. So I'm sure Ketan will tell you his plan.
Yeah, thank you very much.
The first sign that he's using more serious methods is he's using the blackboard.
So the goal of these lectures is to give an overview of this approach called geometric complexity theory to P versus NP and related problems in complexity theory. So the complexity classes that will be concerned with are P and the class of problems which can be solved in polynomial time. In P, the class of problems whose solutions can be verified in polynomial time. And the counting class associated with NP, sharp P, or it should be P to sharp P, and the class NC of problems which can be solved fast in parallel, that is in polylogarithmic time using polynomial number of processors. So the conjecture in complexity theory is that these classes are different. So the P versus NP problem in particular says that the class P and NP are different, and the other problem that we will be concerned with here are the sharp P versus NC problem, which says that those two classes sharp P and NC are different. And this is generally regarded to be a basic prototype of this P versus NP problem, and this in particular is implied by the stronger non-uniform statement called the permanent versus determinant problem as posed by Valiant. And this in a concrete non-uniform, this problem is as follows. So the problem is to show that show that permanent of an n by n matrix cannot be expressed as determinant, cannot be expressed linearly as a determinant of an m by m matrix when m is equal to polynomial in n. By that we mean of the form n to the constant for some constant a, or more generally 2 to the polylog, which means 2 to the log n for some constant this as n tends to infinity. So what do we mean by linear expression? So what we mean is the following. So think of X as an n by n variable matrix, and what we want to show, and by linear expression we means if this is a matrix Y which is m by m of size, small size. By small size we will always mean either polynomial or 2 to the polylogarithmic, and if these are the entries yij's of this and these are the entries xlk's of this, then by linear expression we mean that each entry yij of y is a linear combination. So is of the entries e I j l k is a linear combination of affine linear combination of the entries in X. Okay, and the underlying field of computation is supposed to have characteristic different than 2, and the problem then formally is to show that there do not exist the numbers a, l, k, I, j such that with when the entries of Yi are affine linear combinations of this permanent of x is equal to determinant of y when m is equal to 2 to the log to the a fixed and n is going to infinity. Okay, so this is what the problem is.
Probably
Is that a practice problem?
Huh?
Is that kind of a practice
No,
problem?
no,
Does
no.
that imply anything?
Sharp P is different from NC.
That don't imply that.
Yeah.
If you
No,
do
no.
it over a finite field, then it implies.
Yeah, yeah. So the point is, over finite field, this would imply that Sharp is different from NC, but the simpler version is to take it over characteristic 0, and the version in characteristic 0 is a formal implication of the version in finite field, because if there existed, for example, an integral matrix like this, you could just reduce it mod P. Okay, so generally, so first thing is to consider the characteristic 0 version of this. So this is what we'll do first, and the characteristic 0 version of this can also be similarly defined, that is done in GCT1. Now, all the results that we will talk about and are proved in this approach, the analogues of the main results also hold for this general P versus NP problem, where the role of Sharp P is placed by certain NP complete function and the role of determinant is played by certain P complete function. But since this problem actually illustrates all the basic ideas of the approach, we are just going to concentrate on this with the understanding that the story for P versus NP problem is similar. Okay, so
I just want to mention, it's not clear at all that such a matrix Y exists of any dimension. So that also follows from variant. If M is exponential in n, then the alpha.
Why just the specific symmetric function of the variables? Why are there other functions that have played as well?
They are complete. They are complete.
No, but who sucked this particular one out of it?
this valiant, yeah. Okay, and so this actually we can just take it. This is the affine linear combination. So without loss of generality, we can turn it into a homogeneous problem by just multiplying this, adding by one more variable here z, and then this would be equal to z to the m minus 1 n. Okay, so since this homogeneous form is equivalent to the affine form, we are just going to work with this homogeneous form. Now this in turn is equivalent to the following, that for that what we do is we just expand this matrix X a little. So let us call this expanded matrix X bar, this is n plus 1, and this then becomes the expanded matrix X bar n plus 1, and then this is equivalent to this, that there do not exist numbers a, I, j, l, k in C such that with y, I, j equal to l, k, a, l, k, I, j, this is less than or equal to n plus 1. Now here it was like x bar l, k, yeah, determinant with this permanent of x times z to the m minus n equal to determinant of y. Okay, so this is equivalent, because if this holds, then these things, since they don't occur on the left hand side, we might as well set them to 0. So this is the form that we are going to work with of the permanent versus determinant problem. And so this is the concrete result that was proved in the starting papers of GCT. So what it does, now notice that this, though we use determinant to set this problem, we could have as well worked with traces, because the determinant can be written as a polynomial in the traces, that is there exists some polynomial g w0 to m, such that if you put here traces, trace y to the 0, trace y, etc., trace y to the m, for such explicit polynomial that is equal to the determinant, that just follows from the classical result of symmetric functions. So this is now the concrete lower bound that was proved in the beginning papers of this. So this is the weak form of Sharp P versus NC problem, and what this says is that for any large enough n, that is as n tends to infinity, with m as above, there do not exist numbers b, l I, c, k j in complex such that with y I j equal to l k less than or equal to n plus 1, b l I c k j times x bar l k permanent of x is equal to times z to the m minus n equal to determinant of.
This means that there is no rank 1 linear method.
Yeah. So that this, and there does not exist this and any polynomial and a polynomial g w0 to wn such that this and with this equal to g trace y to the 0 trace y trace y to the n. So, this is a weaker form in the following sense. So, here we are allowing arbitrary constants a l k's. So, here on the other hand we are taking smaller number of constants b l, and all these things are then just pairwise multiplication of appropriate number of them. So, here the degrees of freedom here. So, here for example the degrees of freedom, so the degrees of freedom by which we mean the number of a's here is equal to approximately m square n square, whereas here the degrees of freedom here, degrees of freedom, that is the number of b's and c's here is approximately 2 times n n. Okay, so it's weaker in the sense that the degrees of freedom here is roughly square root of the degrees of freedom here. Okay.
This is impossible for what m? For any m or for?
Yeah. So actually this for any m.
For any m.
Yeah.
So that's really too weak. There's
Yeah.
not enough.
That's why is the weak form. Yeah. So and then in the remaining papers of GCT, a plan is given to leave the proof of this to the general case and to the general case for the P versus NP characteristic 0, and that plan has been partially implemented so far. The implementation is far from complete, but the results obtained so far indicate that this is a quite natural approach, and the mathematical proofs that we seek along these lines ought to exist, but there are considerable mathematical difficulties ahead as to be expected. Yeah. So, now the proof of this as well as the whole plan goes through algebraic geometry and representation theory and so forth. Now, one can ask, why is it necessary to use such non-elementary techniques to prove these kinds of elementary results, because after all there is not a word of algebraic geometry here, not a word of algebraic geometry there. These are all elementary statements in linear algebra. So also that, and so also the P versus NP is an elementary statement in linear algebra, because it can be formulated in terms of integer programming problem. The reason is that though these problems look very elementary at the surface, there are some very hard complexity theoretic barriers that are hidden underneath these elementary problems, and those barriers have to be broken to prove those results, and for that matter even this weak form of the Sharpe versus NC problem. And it is because of those complexity theoretic barriers that we have to resort to all kinds of non-elementary techniques, though the statements are purely elementary. So, in these lectures we are not going to talk about these barriers in complexity theory. So, let us just get the basic idea of the proof technique, and after that if necessary we can discuss the issue of barriers separately. Okay, so what we are going to do now is we are actually going to give the basic plan for this, and then there is one key step for the basic plan which can be completely executed in the weak form, but that key, so we will give an overview of that key step for the weak form during the course of lectures, and then we will give an overview of the plan for executing that key step for the general problem. And so let us begin. So, the basic plan. So, the first step in the basic plan is the following. So, we take this non-existence problem. So, it is a negative statement. So, which is what our permanent versus determinant problem is, and we reduce it to existence problem, which is a positive statement. So, in particular we reduce it to proving existence of a family ON of obstructions. So, what is an obstruction? So, the obstruction ON is supposed to be a proof certificate for hardness of permanent X. And by hardness of permanent X, it means that it cannot be expressed as determinant of Y of size m, and by small size m we always mean henceforth that m is equal to 2 to the polylogarithmic function of n. Okay. So, that is what hardness of X means, and this obstruction is supposed to be the proof certificate in the same sense that, for example, Kurosawa minor of a graph is a proof certificate of its non-planarity. So, of course, this is not going to be a graph theoretic proof certificate, rather it is going to be an algebraic geometric representation theoretic gadget whose existence for every n would act as a guarantee, as a proof certificate that permanent is not is hard. Okay. So, this, and the whole point is to construct these algebraic geometric gadgets. So, to construct such gadgets is done in the following way. So, the idea is to first associate with the complexity class sharp P a family X to the sharp P in M of class varieties, which are going to be constructed using some group theoretic constructions. So, these class varieties are going to be projective algebraic varieties. There is some higher dimensional generalization of familiar curves and surfaces, and intuitively the points on this class varieties would correspond to languages in sharp P intuitively, because there are going to be some other points also added for the sake of compactification and to make it nice. But the first you associate with the complexity class sharp P collection of these class varieties, and similarly with the complexity class this a family X n C n m of class varieties, again group theoretic. So, the idea is that what we are going to do is this is going to be X sharp P n m. Okay, so, such family, and then there is going to be a family X n C n m. Okay, and these families are going to be constructed such that the following would hold, that if permanent of X n by n can be expressed linearly, can be expressed as determinant of Y, this is m by m, then it would follow that X sharp P n m would actually be a subvariety of X n C n m. Okay. So, this is what would happen, that this can then be embedded inside this, and now what we have to come up with is an algebraic geometric gadget which is going to block this embedding. That is what the obstruction is going to be. Okay. So, this is what. So, now, so how are you going to do this? So, the idea is that these are group theoretic. So, the group G equal to G L L square C, okay, so is going to act on these class varieties, and by act we mean just as this group acts on the Euclidean space. So, this L is going to be m square. So, just as this group act, so this is the group of invertible L by L matrices, and so it acts on the L dimensional complex projective space, that is it moves its points around. So, in the same sense, in the similar sense, it is going to move the points of these varieties around. So, since this group acts on these varieties, that variety, the homogeneous coordinate ring of these varieties is going to have some representation theoretic structure, and by homogeneous coordinate ring of a variety we mean the ring of polynomial functions or something like that on the variety, just like we have the coordinate ring of the complex space. Okay, so then an obstruction is good. Now the group theoretic structure of these varieties is going to put constraints on what is going to be the representation theoretic structure of the homogeneous coordinate ring, and the obstruction is going to be a representation theoretic object which can live on this variety but not on this variety. If you can show existence of such an object, then that is going to block the embedding. So that is the idea. So how do we do that? So for that,
What is L going to be? The
m square,
size of the group?
m square,
X?
m square, m
M
square.
Okay.
Is there anything underneath? No.
No, there are two, but you can.
Okay, yeah. Okay, I think let's just.
Your varieties are going to be actually little bits of varieties, GLN only, and acting on some tensor powers. It's never going to get worse than that, right?
No, we'll construct the actual varieties in the next.
Okay, I'll wait.
Yeah. So let's. Okay, because we'll have to go. Yeah, it is going to be some constructions through geometric invariant theory. So we'll have to. Yeah.
Those are the complexity of those
It's huge.
is huge.
Yes, and that the whole point is
Frightening. It's a sort of a frightening.
frightening. The whole point is to get around that frightening scenario. So you are saying, okay, so it can be done. That is what the whole thing is about. To get how to get around that frightening chaos. Okay, so let us recall some basic fact of representation theory. So the classical fact is that the irreducible polynomial representations, by polynomial representations we mean the entries of the representation matrix are polynomial in the entries of the matrix in G. So all the irreducible polynomial representations of G equal to GL LC are in one-to-one correspondence with partitions of length less than or equal to L, and by partition we mean an integral sequence, non-increasing integral sequence like that, lambda L greater than 0. So these are all going to be integral. Okay, so given a partition lambda, what Weil shows is that
Something about the sum of these lambdas?
no, there is no restriction. The length should be at the most length. Okay, so what Weil shows is that corresponding to every such partition lambda, there is an irreducible module G, which we'll call the Weil module, that is indexed by lambda, and conversely, all irreducible representations of G arise in this fashion. These exhaust all the irreducible representation. So these are the Weil modules. Okay, so now we have to use these. So basically, these are the building blocks. These irreducible representations are the building block of the representation theory of the general linear group. Because the complex representations, we can think of them as very complex buildings of which are composed of basic building blocks, which are the bricks, and these are the bricks, and these bricks have various colors. Those colors are these are the labels. Okay, so those bricks have various labels, and all the complex representations can be decomposed in the form of these basic building blocks, the Weil modules, which have all names and colors, so forth. Okay, so now how do we define the obstruction? So suppose that m is equal to 2 to the log a n, a greater than 1 fixed, and n is going to infinity. Now suppose to the contrary, that x sharp p nm is actually contained inside x n c nm. Okay, so suppose to the so now let R n c nm be the homogeneous coordinate ring. So this is the homogeneous coordinate ring of this class variety. So this is the homogeneous coordinate ring, and similar.
A few words about it for those not in, for the complexity theory.
so well, all the regular functions on that variety. So no, this is a purely algebraic geometric notion.
But yeah, but it's captured just for polynomials on the
Huh?
these are polynomials on the
Right, right.
on the variety.
Yeah, yeah, polynomial functions of some, not exactly, the functions are not regular functions, but some, yeah.
Okay, so it's
Yeah.
for intuition, it's
Yeah.
okay to think about
Yeah,
them
yeah,
as
yeah.
polynomials.
Functions on the, yeah, and similarly this is going to be the homogeneous coordinate ring of this class variety. Now if these were actually contained in that, then by basic algebraic geometry it follows that there would be a surjective map from this homogeneous coordinate ring to this homogeneous coordinate ring, which is basically just given by restriction. So that if this x sharp p is contained inside x and c, then you can just restrict the functions on this to this, and that is going to be a surjection. And not only that, that surjection is going to be degree preserving. So if this is the degree d component of this, then there is going to be a surjection onto the degree d component of this, and by dualizing this, what we will then get is x sharp p n m d dual can be injected into r n c n m d dual. Okay, now by the reductivity by Weil's thing, now this is a very complex representation. Now, but by Weil's result, this complex building can be now decomposed into the building blocks. So our obstruction is going to be a representation which can occur here, but which cannot occur here. Now that is going to be the obstruction. So let us. So this is the crucial definition.
What will be the dual of this
Just harm. Just the functions from here to the complex numbers. Yeah. Yeah. So definition.
So the d we can think of the degree as a polynomial function.
Yes. Yeah. So for every day you will get this, and obstruction is going to be an obstruction On. Obstruction On is a Weil module V lambda g that occurs as a sub representation in R sharp P NMD dual, but not in R NC NMD star, and it just follows from absolutely the definition that the existence of an obstruction On, such an obstruction On for all large enough n, when we have m equal to 2 to the log a to the n a fix, implies that perm x cannot be expressed.
This is going to be given by some very complicated branching rules, right?
No, extremely. So they're not. So that is going to be one of the hard problems, how to get those branching rules. Okay, yeah, but not the known ones. So we'll have to. So determinant y.
I mean, that's the kind of combinatorics that you're trying to understand.
Yeah, you want to understand, but yeah, but that combinatorics would have to be. We will have to go through algebraic geometry representation. Yeah.
In this statement, is this statement true for every m, or only m's going up to this?
No. Otherwise, if m is like 2 to the n, the obstructions are not going to exist. Okay.
Maybe they will not, but just the fact that existence implies that you cannot.
No. So the existence for any function of m, as long as obstructions exist, that would serve. But
Existence of a function
yeah.
implies it, so you
Very
can
well.
remove this.
yeah, amen. Yeah. So
Good. I want to see at some point how the boundary come in,
yeah,
because we know
yeah,
that.
yeah. So now the goal now is no. So it's the obstruction for some d that occurs for some d. Yeah, that's all. Yeah. Yeah, the degree generally would be can be expected to be polynomial in, yeah, but yeah.
So could you be unlucky in the sense
Hmm?
that could it be that there are no such obstructions?
No, but that is what the whole the thing, the results say that actually the obstructions would exist, assuming that what we want to prove is true. You know, so that is what. Yeah, sure. Yeah, so I mean that is what the. Okay, so now the goal is that we'll see in the next. So the goal now is you want to prove an existence of an obstruction family ON, and for this of course now we are, in fact what you said is a very precise point. Like if instead of permanent and determinant we were to use some other functions in Sharpe and NC, then almost always the obstructions won't be there of this kind. So the functions have to be, if instead of,
What's so great about permanent and determinant?
yeah, so that's what I'm going to say.
See, from algebraic geometric point of view,
Yes,
how
it-
do you ever single these things out?
Okay, so using exceptional nature of, so that's what the next thing, exceptional nature of permanent x and determinant. So it is going to depend on this and determinant y. So what is so great about permanent and determinant? Yeah, so that is precisely the point. So first of all, the permanent, as we know, permanent of x is equal to, within a constant factor, is the same thing as permanent of AXB for all AB which are diagonal or permutation matrices, diagonal or permutation matrices, and x is equal to either x star is x or x transpose. So that is the obvious property, but what is important is that among all the polynomial functions of degree n in the variables of x, this is the unique function with that property. Okay, and this can be proved using some classical representation theory. That is what is so exceptional about it, that it is completely characterized by its symmetries. And similarly, something exceptional about determinant of y, the determinant of y is equal to determinant a y b transpose for all a b inside GLN MC, and again y star is equal to y or y transpose. And the important, so that is the trivial part. The non-trivial part, this is the classical invariant theory, which says that this is the unique such function of degree m in the entries of y which has this property. So what exceptional means is that it is, exceptional means is that it is completely characterized by its symmetries. So if we were to start with some other function in Sharpe or NC which does not have this exceptional property, this whole approach is going to collapse, and in fact the obstructions would not.
But your whole approach is to introduce much more complicated invariant theory to deal with these two. As you say, this is simple.
Yeah, this is simple.
You're about to introduce is very complicated.
Yeah. So the whole approach is to use this property. So the whole approach is to use this exceptional property to prove existence of these obstructions. This is what the main goal is. Okay, so now, so this is the first.
Is that how you get around the naturalization?
Yeah, because this is a very exceptional thing. Yeah. No.
Well, I mean, there are two techniques where you could prove that there's something on that is low bounded. It has to apply to a very large number of functions. Presumably, the approach is only going to have these.
Okay, so now comes the first theorem.
And it's very hard to prove anything that applies to only the
Okay, so the first theorem, there exists such a family of obstructions. So this gives us assurance that we are going in this family of obstructions, this in the weak form of the permanent versus in the weak form of Sharpe versus NC problem. And in fact, this proof technique is going to give these obstructions more or less explicitly. Okay, so in the weak form of the permanent in the Sharpe versus NC problem, such an obstruction family exists, and for every n you can actually nail down what that obstruction is. Okay, so and this, of course, this theorem immediately implies the weak form of the Sharpe versus NC problem. So that is how the weak form of the Sharpe versus NC problem in characteristic 0 is proven by proving existence of. So so what is the basic idea of the proof?
So just a second. What is the role of L? L you said was the size m squared, right?
Yes.
This theorem will be true regardless of m.
Yeah. For every m greater than n.
Every m
Yeah.
greater than n.
Yeah.
So you will have to present such a family of obstructions for every m and every n, for every n and every n.
Yeah. So how does the proof go?
But when in the weak form, you assume that embedding is a special structure.
Excuse me?
In this weak form, you assume that.
Yeah, so the point is, yes, so in the weak form, again you construct class varieties, the analogous class varieties and the analogous notion of obstructions, and again all those have exceptional structures, and that is what is going to be used in the proof. So we are not going to go into the proof of this, which goes through geometric invariant theory. So it is based on the following things. So the
form is basically that the linear mapping, the projection is 1 to 1.
yeah, okay, so the proof goes on the following thing. So the first is the work on stability in geometric invariant theory. So that is the first thing. So GIT. So the first thing is we have to see what is this. These class varieties are all of exceptional kind. So what is the nature of group action on these varieties? And the stability was fundamental notion in geometric invariant theory that was introduced by Hilbert in the beginning of the last century, and that work was extended by Mumford to construct moduli spaces in algebraic geometry, and further by Kempf. So that work on stability in geometric invariant theory is the first fundamental component that is required to understand the group structure of these varieties. And then second, of course, the harmonic analysis on the unitary group. So in the form of the Peter-Weyl theorem, or the algebraic form of that. And third, some geometric representation theory. So by that we mean some generalizations of the classical Borel-Weil theorems to these class varieties.
Hilbert's work was actually exactly the opposite. He said you should never compute, but he proved existence.
Yeah.
He put the subject to rest for 70 years.
Yeah. So
It took Mumford to resurrect.
yeah. Okay. So these three things together give us a good idea on the representation structure of these class varieties in the weak case. That is basically what kinds of representations Weil modules can occur on this, and what kinds of representations can occur on this, and then using that one can just nail down and actually spell out an obstruction O(n) for every n large enough. Okay, so that is how. So now the thing is, now we want to go from, of course, the weak to the general case. Okay, so
You're not going to explain that more?
no, not today. In the tomorrow, because we are not in these lectures. We are not going to assume familiarity with algebraic geometry representation. So little bit, we'll go into that little bit. Yeah. So yeah.
What about the weak form? I mean, do you think that these tools are necessary for the weak form?
Yes.
Weak form is
Yeah. Oh, no, weak form is because for weak form, those fundamental barriers like natural proof barrier, relativization, and algebraization, all those have to be crossed even for this.
why?
We will see in the course of things.
Also, can I?
In the course, we'll see.
Third or standard. The second, what's the harmonic analysis of it? Just to give a word. What kind
Peter-Weyl.
Yeah, what are you using there? Oh, Peter Balfour.
Yeah, Peter-Weyl.
Okay, so completely standard thing.
Okay. Yeah. So even for the weak form, all those things are required because all those three barriers have to be. We'll see in the course of. Yeah. Okay. Now the general case. So now, how do we go from the weak to the general case? Okay. So that is the main thing. So for that, what we are going to do is we are going to introduce some representation theoretic functions which are associated with these class varieties. So, how do we associate such functions? So let us denote this function if lambda n m k. This is defined to be the number of occurrences of v k lambda g. So, given a partition lambda, we can simply stretch it by a factor of k by multiplying every integer in that sequence by k. Okay. So, the number of occurrences of this wild module corresponding to the stretched partition function in the homogeneous coordinate ring of Sharpe. Okay. So, basically if we just start with lambda, then we stretch it 2 lambda, 3 lambda. So, this is a statistical functions which measures how many occurrences of this in the coordinate ring of that class variety and so forth. And similarly, we will g lambda n m k is equal to the number of occurrences of that wild module in R n c n m. So, this is the key result of GCT. So for to go from the weak to the general thing, this is the key result that would be needed. So, theorem 3 GCT 6, that if lambda n m k and g lambda n m k are quasi polynomials, assuming that the singularities of the class varieties are rational.
Polynomials in quasi-polynomials in which variable lambda?
In k as a function. So, what are quasi polynomials? Quasi polynomials, will define them precisely in the next. Quasi polynomials are hybrids of polynomials and basic periodic functions, constructed by polynomials and basic periodic functions by multiplication, addition, subtraction, etc. And rational means that certain cohomological objects that are associated with these singularities all vanish. And there are actually the main results of GCT 6, which, because these are group theoretic constructions which actually say that this actually singularities ought to be rational. So, we will go over that. So, this is a reasonable hypothesis, assuming that it says that all these representation theoretic functions are in some sense the periodic polynomials. Okay. So, there are this proof. So, this is the crucial fact that will be required, and this is based on the proof of this is based on the first will require.
So we assume that there's an assumption here.
Yes, that the singularities are rational, and that assumption.
Then you're going to get this
Yes.
strong form of that.
Yes, strong form, and for that assumption then there are results which would justify that. So, this thing is based on first will require the resolution of singularities in characteristic 0. So, this is the fundamental work of Hironaka and some cohomological works based on this. So, as you said, this rationality is a cohomological constraint, and what these Hironaka gives a way of resolving these singularities in characteristic 0, and what these cohomological works say is that starting from this variety, if you get new varieties by taking quotients with respect to group actions and so forth, those varieties would also have nice singularities, and it is finally a detailed study of the singularities of the class varieties and the new varieties obtained from them using group action. So, using that we can get that these things are very special functions. Now, what is the use of that?
Is that assumption that you have in theorem, is that part of some standard conjecture that other people have made?
No, so some weaker form of that actually we prove of this conjecture.
But this is not being formulated by people who work.
No. but some weaker forms of this using the thing will prove. So we'll okay.
Are you going to say something about the construction of the varieties so that we understand what
Yes, but for that we will have to go through something. So that I'm going to do tomorrow. Okay.
tomorrow? But there are the points in them we should think of as languages in this complexity class.
And something
or
more,
as
and something,
compactification.
and compactification. Yes, we are going to talk about them. But let me just first give the overview today. I mean, what we are going through for the general thing, and then we'll begin on the constructions tomorrow. Okay, so fine. If these representation theoretic functions are so nice, now of what use are they to us? So for that, first let's recall the notion of an Erhard quasi-polynomial. Erhard quasi-polynomial of a polytope P, and this is defined to be, so this Erhard quasi-polynomial will denote this Fp by k. This is defined to be the number of integer points in the dilated polytope k times p, and it is a classical result of Erhard that this function is actually a quasi-polynomial. And now the point is that in geometric representation theory, whenever a fundamental representation theoretic function turns out to be exceptional, that is, it is a quasi-polynomial, then it so happens that generally it has an interpretation as an Erhard quasi-polynomial of some polytope. Okay. So given by that message of the geometric representation theory, we will formulate this positivity hypothesis. And so what it says, positivity hypothesis is that akin to the story, recurrent story in geometric representation theory, here also there exist polytopes P lambda nm and polytopes Q lambda nm for given lambda nm such that if lambda nm of k is the Erhard quasi-polynomial of this polytope. Yes, and similarly g lambda nmk is the Erhard quasi-polynomial of this polytope. And these dimensions of these polytopes, dimensions is guaranteed to be polynomial by some results in this GCT, guaranteed to be polynomial. Excuse me?
Under the assumption that you made here, right?
Yeah, so if these polytopes exist,
And then you're using a standard kind of hypothesis, which means that the quasi-periodic functions are Erhard.
yes. Yeah. So this is assuming that, yeah. So that there exist polytopes such that, so what this says, this is called positivity because it means that this function has a positive interpretation as the number of integer points in a dilated polytope. There are no alternating signs, and it is a positive convex interpretation. Okay, so this is a positivity hypothesis, and if these polytopes exist, then the general results would actually guarantee that their dimension would always be polynomial. Okay, in the parameters. So now what is the use of this to us? Excuse me, this positivity hypothesis? Oh yes, no, and the main work of this thing actually gives an approach to prove this positivity hypothesis. So we'll come to that in few moments. Yeah. So assuming this, okay. So theorem for GCT 6, and this is the easy part. I mean, that is the main result really, that there exists an explicit. There exists a family of obstructions ON for the general problem, okay, for the general Sharp P versus NC problem in characteristic 0. And actually the analogous result also holds, though we are not going into P versus NP problem, but the analogous result also holds here, and P versus NP problem in characteristic 0, assuming first the positivity hypothesis P of H, that, and what we will call the obstruction hypothesis, which basically says that for all n going to infinity, and with of course m is equal to, as usual, 2 to the log a n, a greater than 1 fixed, it is the case that there exists lambda such that p lambda n m is not empty and q lambda n m is empty. Okay. Now, one can see that once we have gotten these polytopes, then using this one can easily, because what one says is that these polytopes determine this function, these polytopes determine this function. Now, if for every n there exists such lambda such that this polytope is non-empty, then we can take some dilate of that lambda, so that that dilated polytope is actually going to contain an integer point. Okay.
But if it's empty, then it's 0.
Hmm?
If it's empty, then G is equal to 0. If Q is empty, right?
No. For that particular value of lambda. Oh, yeah. Okay. So we are going to choose lambda, okay, such that actually this polytope is, one is non-empty and the other is non-empty, and the other one is empty. And then by choosing
You could take any models when you
any integer point, so that would mean that if you stretch lambda anything, that the while module vk lambda is not going to occur in the class variety for NC, but the while module k times lambda is going to occur in the class variety for Sharpie, and then that is going to nail down the problem. Okay. So the whole thing is now the proof, how to prove why. First of all, there are two important problems here. So first, so the strategy is assuming this, the strategy is very simple. So first find explicit p lambda nm and q lambda nm to prove pH. So you prove pH by actually finding such explicit polytopes, and then once you have this, then the strategy would be then find an explicit family lambda n satisfying OH. And then the understanding would be that if you just stretch these labels, partitions lambda by some factor k, that is going to be our obstruction. Okay.
So the only reason you said that you got this assumption about the singularities being rational is to motivate this assumption. To motivate the
Yeah.
assumption. Just motivation. So you don't need this for your
No, but the point is, if the thing were not even quasi-polynomial, the polytope is not going to exist in the first place. Yeah. Yeah, I mean, for a polytope to exist, the function has to be quasi-polynomial in the first place. Okay, so.
But as long as it's quasi-polynomial, you don't care about this beginning.
Yeah.
I think he's trying, which I'm also trying, and maybe others are also trying to understand what you're assuming, what you're not assuming, what's reasonable to assume, and also what's purely something about polytopes, purely combinatorial, and what's really representation theoretic.
Yeah.
You seem to not be explaining that to us.
No, I'm going to do that. Yeah. Yeah, of course. So the quasi-polynomiality result is required to motivate this positivity hypothesis, because without that the positivity hypothesis simply collapses. Okay, that first of all, two sets of results are required: the results to justify why the singularity should be rational, then assuming that this guarantees that it's a quasi-polynomial, so then we can formulate this hypothesis.
So then this last part, that was his question,
Yeah.
has little to do, it's purely combinatorics about polytopes or not?
The last part, meaning this OH.
No, that part I have no understanding. That seems to be assuming what you want to prove almost. But
Yeah.
let's say the positivity hypothesis,
Yeah.
which has been proved in some cases.
Yes.
maybe in
Yeah.
dispute.
yeah,
presumably you need it much more generally.
yeah, yes, yes,
So that maybe fits into a sort of standard program.
yes, yes, yes.
But I'm trying to understand whether that's a positivity, a conjecture hypothesis that's connected with representation theory or with convexity of polytopes.
No, so this positivity hypothesis is in fact intimately connected with the representation theory. In fact, the approach to prove this positivity hypothesis, I'm just going to talk about that, would go through this representation theory of quantum groups. So it's a purely representation theoretic thing. Yes. Okay. So, and we'll see in a moment why we require this. So the idea is to prove this positivity hypothesis, get those polytopes, and then after that is the combinatory. Then use those polytopes to just nail down the.
Could you say a word about this OH? Is that, because that seems to be less standard.
Yes. Yeah. So.
That's an assumption, right?
Yeah, that's an assumption. Yeah. So first of all, so the first thing is why should pH and OH hold? Yeah. So. I mean, so most of the results go why should pH and OH hold, right? I mean, a priori it is not clear why they should hold. So.
Nothing's equivalent here.
Huh?
If they fail, you learn nothing. Is that correct? It's not. There's no equivalence. Meaning, if they are false for some reason.
No. Yeah. So why should so actually the main work here is so the main mathematical evidence which we will talk about in the remaining two things. So the main mathematical evidence. So this is given in GCT 6 and 7, 8 and 2. And the concrete evidence here is that actually this holds in the weak case. That is how actually the weak case is proven. Weak case. So this is how actually in the weak case you prove pH, then you prove OH, okay, and that is how you actually nail down the obstruction. So there is something to start with, okay. So this is a concrete thing that this is how actually the weak case is proven, and those pH and OH are actually natural generalization of what is proven in the weak case. So we are going to go through the proof of the weak case because that is important. Without that, why pH and OH should hold would not at all be clear. So that is actually the basic prototype. Why such positivity hypothesis and obstruction hypothesis hold, and then we'll give an approach to actually lift that proof from the weak case to the general case. So the weak case is very important in this whole approach. Yeah.
So again, I want to ask about the distinction between the weak case and the general case. The weak case, the lower bound or impossibility holds regardless of the value of m.
Yes. Yes.
And in the general case, the value of m, the factor
No.
has to come in.
Yeah. So M is in the weak case. What happens is that polytope, okay, this polytope actually never becomes empty. So in the general case, there would be more constraint that after a while, when M becomes thing, it will become. So.
Do you have an explicit construction of polytopes that you just can prove that they are the right ones, or you?
Yes. For the weak case, for weak case.
For the general case.
No, for the general case, there is an approach to construct those explicit obstructions to quantum groups. That's what I'm going to. But in the weak case, everything can be done explicitly using the known representation theory. And it's just that in the weak case, okay, so that condition keeps on holding all the time. Okay, this keeps on remaining non-empty all the time. Whereas in the general case, when M is large enough, that there will be more constraints added because the degrees of freedom is less in the weak case. So there will be more constraints added. After a while, it would become non-empty. Okay.
Why do you expect it will become non-empty?
Because there are results.
No, there are
Oh, yeah.
You see,
Yes.
it's clear that if m is 2 to the n,
Yes, the obstruction.
no.
Yeah, of course. So all the main results actually is about why pH and OH should hold. I mean, So and all I'm saying is that in the concrete case, you can see that the technology is working. Okay, so the.
Right, you mentioned that assuming that Sharpie is different from NC, then
The obstructions of this, so there are results of the kind which says that if Sharpie is not equal to NC and some reasonable mathematical assumptions for which the evidence, then actually these obstructions would exist and this pH would hold. So like that, but that is not going to help us in proving pH. Rather, it gives us an assurance exactly of this kind. The results are exactly of this kind, that assuming what we want to prove finally is true, then there is a reasonable assurance that all these hypotheses are going to hold. Okay, but of course the whole point is to prove it without assuming what we want to prove. Yeah. So.
Yeah, that's why I asked you equivalence. It's not the P equals NP problem there.
Huh?
Some other intermediate things that we will have to believe. You said assuming what we want to prove is true. But you want to prove is P is not equal to NP.
Yes.
That's not,
Or the Sharpie.
it's not equivalent to that problem. This
No, no,
is-
it's not
you
equivalent.
need you need some other things to be true,
Yeah.
which we have to get a feel of how reasonable.
Yes. Okay. So now, so the first, why should pH and OH hold? And the next thing is how to now in the weak case we can see that the hard part actually is to get pH, these polytopes. Once you get those polytopes, then it's just the combinatorics. So this is the hard part, and this actually is the easy part once you get hold of this. So the thing is, the same picture is expected to be in the general case. So the hard part is now how to go about getting those polytopes. That is what, and what are the results, which partial results which say that these polytopes should exist and so forth. Okay, so that is the. Yeah, so in GCT 6, so how to prove pH, and also these results would also give evidence why pH should hold in the first place. Okay, so all that evidence. So the basic plan for this is basic plan is given in GCT 6, and it is partially implemented. Implemented in GCT 478. So we want to give some glimpse of that stories. Yeah, so this is what we want to do finally. Yeah, so we have, in the weak case, we know that the pH, the kind of pH that we want holds. Okay, and now we want to jack it up to the general case. So what we want to do is jack up this pH in the weak case to the general case. So how do we go about doing it? Yeah, so for this jacking up procedure, what actually we need is this lifting procedure is some kind of an inductive process. So what we need is some stronger form of pH for this inductive process to work. So let's what this stronger form of pH is, I'm going to state in the remaining lectures. But what that stronger form of pH says is that the representations of that general linear group have some explicit basis with some exceptional properties. Okay, and that stronger form actually more or less implies pH. So this stronger form is what is required for lifting process, though it is not required for the weak thing. That is why weak is weak. So you don't require all that hard thing. Now the only proof of this pH star goes through the theory of standard quantum groups. So this is how quantum groups would come into picture, that the stronger form of pH that we need for lifting process actually goes through. So what is quantum group? So quantum group basically is a mathematical object that was introduced in theoretical physics. So when we want to combine quantum mechanics with relativity and so forth, what you require is a mathematical object which will play the role of the general linear group in quantum mechanics. And quantum group as constructed by Drinfeld and Jimbo are those standard are those mathematical objects. And a fundamental result in the theory of quantum groups says that the representations of these quantum groups have something called canonical basis. So these canonical bases were for the representations of the quantum groups were constructed by Lustig and Kashiwara, and they are intimately related to the similar canonical bases for Hecke algebras, which are dually paired with quantum groups by Kazhdan and Lustig. So these canonical bases have precisely those exceptional properties that we need to get this pH.
Is something that you proved?
In this weak case, yes. In the weak case, not proved. I mean, actually, just follows from the results of Kashiwara. Has been proved by Kashiwara and Lustig. Yeah. So actually, just using the exceptional properties of Kazhdan-Lustig basis and Kashiwara-Lustig basis, that pH star actually follows. Okay, and that from that pH star, pH also holds, and pH star is precisely the property that you need for this lifting process. So what you want to do is go from now the only proof of that pH star here actually comes through the Riemann hypothesis or finite fields. So that is how the connection with yeah.
That's amongst all your hypotheses, that's not a hypothesis.
Yeah, that's a theorem by Deligne based on the work of Grothendieck. And that is of course a deep positivity statement, that all the zeros are lined up, and it's also some kind of a positivity statement. Using that positivity statement, this positivity statement can be deduced by using the theory of quantum groups and canonical bases as a transportation vehicle. Okay, so this is how the bottom row works. From this positivity hypothesis, run it through this transportation mechanism, deduce this P star. And at present, this is the only way you get the property of P star, because you really require that positivity statement in the full form. So now we really have no choice. If you want to lift this story up, somehow you have to take this bottom arrow and lift it up. Okay, so no. So this part is done. So this is the non-standard quantum group. So of GCT 7 and 8 quantum group. So what it does is 4, 7. So what it does is takes this construction of Drinfeld-Jimbo quantum group and constructs the appropriate quantum group that would be required at the general level, which would play the same role as these quantum groups play at this level. Well, not completely, you need something more than that. This is half the story, but this is really the crux of the matter. So and the remaining is more of the same. So this part can be lifted. So also this. So this.
I'm going to ask you this question about everything you said.
Yes.
Does the value of m matters in this step? The value of m matters in this step, in the generalization of quantum groups?
No, in the generalization of m, no. Finally, it is just going to matter in the constraints here. Okay.
Okay, so it doesn't matter in pH though.
No, just in the way.
Can I understand? The reason you keep asking this question is if his proof had to work without that condition, then it couldn't be correct.
Yes, exactly. Because m equals 2 to the
No.
I want to know where it's
No.
Also because, like typically in complexity or like qualitative statements that are independent of M are much easier than statements that actually depend.
Yeah, but I'm sure what he's telling you is that in this representation theory, once some tensor power is big enough, then you will not have that feature, and that's sort of standard in representation.
Yeah.
That does change.
Yeah. Oh yeah.
He does seem to have a good idea.
Thank you. Okay, so now this canonical basis, this construction can be generalized to non-standard canonical basis, and this is the work in GCT 8. But what is conjectural is that we cannot prove that these canonical bases, the explicit algorithm that is given in this thing, actually have those exceptional properties. Okay, which is the main work of Lustig, based on Riemann hypothesis and Kazan-Lustig, that they also have the appropriate exceptional properties from which then these things would follow. Okay, but we can't prove those exceptional properties. Well, so now the point is, if we now this is like a commutative diagram arrow chase. Okay, so if you now if you want to fill this thing, what is required here? What is of course required here is this. Okay, so what is required here is non-standard RH. We don't know what this is, and we can't. Okay, so.
Certainly not the ordinary Riemann hypothesis, right?
No, but there is a good evidence for this. So let me give. So what is a good experimental evidence for this? So that what we require in this corner actually exists, though we can't prove it. So the good experimental evidence. So the point is.
Hypothesis is that there is a hypothesis.
Huh?
I mean, that's what you're saying, because we don't know what.
No. We not only we can't formulate it, and of course we can't prove it, and both. Okay, so that is beyond our expertise. But what we can give at this point is a good experimental evidence that what is needed is actually there. So what is the so the point is, this deep property of this canonical basis is that its structural functions are all positive polynomials. So these are the Kazan-Lustig polynomials, and their coefficients are all non-negative, and that positivity is actually how is proved using the Riemann hypothesis or finite fields and the theory of pervasives and so forth. What one can do is one can similarly compute several structural constants associated with this canonical basis, and sure enough they all turn out to be positive. Okay, so the point is, these structural constants, the algorithms are huge exponential complexity algorithm. If there were no reason for them to be positive, with the probability half, each constant would be either positive or negative. If all the 1000 numbers turn out to be positive, then one can be fairly sure that the probability of error would be 1/2 to the 1000 or something. It is absurdly small, that there is some deep cause behind that positivity. And we know that whenever this positivity is a very exceptional and rare phenomenon.
This means you've computed these constants
Yes.
for small dimensions.
Yes. And they all
They may change with dimension.
no, the positivity is a very rigid property, because if you compute and it's fairly non-trivial examples, that if there were no cause for positivity, you will see all kinds of patterns, and that positivity seems to be a good assurance that what is required here actually is there, but well, we don't have the mathematical expertise, as we said, to even formulate them, let alone prove them, but it is our hope that the fields of complexity theory and mathematics will join hands together and shed light on this, the hard part. Okay, so what we have done so far is the easy part, and the hard part is that. So
But you talked to Kasdan.
Yeah,
He
yeah.
also has no idea what to formulate as a.
yeah. So I had talked to the experts, but they all believe that all the evidence suggests that what is required is there, and so there had to be a geometric reason for it, and it just that geometric reason. This is P versus NP problem. So there was always going to be a twist to the stories, that the existing technology is not enough, but what is needed seems to be there. So what is there in that corner there? That is the big open problem. So I hope to have given a high level picture, but as we said, we haven't really even defined the class varieties, and so from the next lecture we will actually explicitly construct what those class varieties are, why should pH and OH hold, and so forth, all the mathematical results, and we will start elaborating on this picture. So that will start tomorrow. But yes, separately, not in these lectures, but yes, separately, those algebraic geometry is interested in the construction of non-standard quantum groups and canonical basis and all.
This is a non-complexity question, a very basic question. What's the feeling about this NP of the complex P equals NP, not in finite characteristic? I mean,
No. So the point.
Is this supposed to be?
No, so that is much harder. So as we said, we have to go. The whole point is there are much. For example, one of the things that we use in the
I
proof.
understand your methods use characteristic zero.
Absolutely. Yeah.
But I'm asking just from a complexity theorist point of view, if somebody actually shows that P is not equal to NP in this
Yeah.
zero
Yeah.
characteristic setting, what's the feeling?
So what that means is that as long as you don't manipulate the bits in the memory, okay, that you can't. So you don't take, for example, like in permanent versus computation of permanent, you don't take exclusive or of two things like that. Then there is no natural algorithm.
Is this being formulated
Briefly,
as a separate
there's a general feeling that the algebraic case should be easier than the Boolean or finite field case.
Yeah.
Nevertheless, we are at a loss for proving any results over the reals or the complex numbers as to lower bounds that are slightly superlinear. So we are in the same, same mud.
Since you have so many classes, why is this not another class? You got so many
Because for a very obvious reasons, more of our the problems we need to solve are discrete, constraints, abstraction, integer programming. There are problems about finite field values. The problems the world needs to solve are about finite objects. So that's the reason, but people have been trying for a long time, putting lower bounds on the, over the reals for, let's say, arithmetic circuits, and we are stuck there too. So that
This would show something like these classes do have names, they're just more obscure, right? and so
No. I think the permanent versus determinant, the characteristic zero version is actually a weaker implication of the finite thing. So whatever proves that is going to prove this anyway. So the obvious thing is to understand the easier thing first. This is the easy part, and then worry about the harder part.
this would prove, even if you just did the characteristic zero case, that would show that the permanent has no small
Yes,
algebraic formulas over the.
Yes.
Oh, okay.
Yes, and
So that's already a major.
Yeah.
It's interest
Yeah.
in and of itself.
So yeah.
Are the intermediate problems between the weak and the general, like if the mapping is rank 2? Can you solve?
For the mapping is what?
So the weak version is when the embedding is of rank 1.
Yes.
So
Yeah, sure. Things like that.
does your approach
Yeah, you can go.
Can you do rank 2?
Huh?
Can you do the rank 2?
Ra-
I'm not sure at all. I'm not, yeah. I think rank 2 can be much, much harder than rank 1.
No, anyway, so as we go, we'll see exactly what has to be proven and so forth. And the whole point is that this technology works in a weak case is a good concrete evidence that that this bottom thing works. Otherwise, there would be nothing to lift. Okay, so it is very important that the bottom arrow works. Okay, so that is the base case. And yeah, yes. Yeah.
Okay, so this was around NC and Sharpie, right? Because
Also for
they-
P versus NP, we haven't gotten into the story, but there are analogous theory for P and NP also.
Yeah, that's somewhat mysterious because you need these properties of determinant.
Yeah, so there are some, you have to construct some similar functions with similar symmetry properties in NP, and so that has been,
It wasn't mentioned today, I mean.
no, it wasn't mentioned today. So because we are permanent versus determinant actually shows all the difficulties, so we are just going to concentrate on that. Yeah.
I'll ask the sort of counterpositive to Avi's question. If n is small enough, does your program work? So if say, I think we know that m
It's
has
at
to be
least
n squared.
yeah.
So if m is n plus 1.
No. So see, the point is that there, that the n square lower bound, okay, that would actually not pass the natural proof barrier, because that proof technique would actually work. So how does that, you're talking about the n square lower
No,
bound.
but I'm not saying, so I'm just saying, say you take that proof, right, and you translate it into your model. So you can't imitate that proof and hope to get a non-natural proof. I understand that. But
No, this as present,
you can still show that because by imitating the steps of that simpler proof structure within your more complicated one, you can get a construction.
no. So
value.
in this approach, the thing that can be proven unconditionally is this part, okay. And after this, to get anything, actually the whole thing is such that then it's not really going to matter. I mean, once the thing starts working, it would start working, but till then,
You don't think it's at all worth looking at small values of
no, I don't think that, because we have to use, I mean, as we go over the kind of representation theoretic problems that arise, solving it for n square value or is one and the same actually.
No, he's asking maybe it's not
You
what
could
he
skip
was.
all the. Maybe you could just skip all the steps, just a reality test. Does the obstruction exist for some trivial reason?
No, not trivial. No, we can't. I mean, we can prove only this, but even that is not a trivial thing. I mean, even for the weak case, rank 1 case.
No, so forget weak, just a general case, you want to prove an m plus 1 lower bound. M is at least n plus 1. Now, we know you can prove it. There are several proofs.
Yeah. But
So if you try to just get them through your machine,
no,
it
because I
will
think
not.
no, it will not. Because I think what you will have to do is prove those pH and OH, and that would require solving some deep representation theoretic problems. And
Even
it's
for m. it was
yeah.
n plus 1.
I mean, it is not sensitive to that kind of thing. So it is really, I mean, yeah. So I think we'll begin on elaborating of this approach tomorrow. I mean, including why pH, OH should hold, what these class varieties are, and so forth tomorrow. So thank you very much for giving me a chance. Okay.
So tomorrow is 10:30, and for all of you who want to solve this problem, K